Hello and welcome to another interesting chemistry episode. So we'll continue looking at our series on the atomic structure. Previously, we looked at the atom, the parts of an atom, three fundamental particles of an atom, the characteristics of the three fundamental particles, and how to determine the protons, electrons, and neutron numbers. So we continue from where we ended, and in today's segment we are going to look at those objectives. So we're going to learn how to draw the electronic structures and how to write the electronic configuration. So straight we go into the details. So what is an electronic structure? So what is an electronic structure? So I'm sure you have seen somewhere in the books. Let me use whiteboard. So I'm sure you have seen structures such as this, and then they come with electrons like that. So this is what we call an electronic structure. So in our today's session, we're going to look at how to draw these electronic structures and understand the maximum number of electrons that are supposed to be occupied by each respective shell in an atom. Remember, we talked about the parts of an atom, where we said the central part is the nucleus and the peripheral part of an atom is the shell. So we want to understand how to construct the electronic structure. Where do these structures come from? So that is the objective for our today's class. So basically, the electronic structures, they show the arrangement of electrons. There is a systematic manner in which electrons are arranged in the shells of an atom, and that is what we really want to understand in our today's segment. So to start with, there is need for us to understand the number of electrons that should be occupied in each respective shell. So we have to calculate the number of electrons, or we have to determine the number of electrons that should be put in each respective shell. So if you're talking about the first shell, what is the maximum number of electrons that should be put in the first shell, in the second shell, in the third shell, in the fourth shell, and so on and so forth. So going back to the whiteboard, so how do they come up with, okay, allow me to clear, yeah. So to know the maximum number of electrons that should be allocated in a certain energy level or in a certain shell, we use the formula 2n squared. 2n squared, where a 2 is just a constant, then 2 up there is just the power, and then the n represents the number of shells. Number of shells. So if we want to know the maximum, I'm talking about the maximum. If we want to know the maximum number of electrons, now I'm going to use this. If we want to know the maximum number of electrons that will be occupied in the first shell, in the first shell. This is how we determine it. So in the first shell, the N becomes, so the N is equivalent to 1. So substituting the N in the formula, we get 2N squared becomes 2, 1 squared. Then, so this is 2, 1 squared is 1, 2 times 1 is 2. So the maximum number of electrons that can be occupied in the first shell. Let's look at this. We use black. Let's use this. The maximum number of electrons that can be occupied in the first shell. So if this is our first shell, the maximum number of electrons that can be occupied is just 2 electrons. 2 electrons. So the first shell can hold the maximum of 2 or less. So you can put 1, but the maximum it can hold is just 2. Let's use some formula to determine the number of electrons that can be put in the second shell. So in the second shell, it means our N is equal to 2. So substituting the 2 in the formula of 2N squared, it becomes 2 squared. So 2 squared is 4. Then 2 times 4, we get 8. So meaning that the maximum number of electrons, remember we're talking about the maximum number of electrons in the second shell should be 8. So if we look at the maximum number of electrons, this is our second shell, therefore the maximum number, let me use a different color, maximum number of electrons should be 1, 2, 3, 4, 5, 6, 7, 8. Then let's go to the third shell. Let's go to the third shell. For the third shell, applying the same concept. So third, use a different marker. Use black. So for the third shell, we say third shell, our N will be equal to 3. Therefore, 2N squared comes 2, then 3 and squared. So this will be 2, 3 squared is 9, then this will give us 18 electrons. So the calculation goes on and on, but because we focus on just the first 20 elements, then 18 is basically enough for us to kickstart. So what happens here now is the 18 comes with conditions. The 18 comes with conditions. But let's draw this structure. So the 18, okay, let's take it. This is 10. So the 18, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the third shell should hold the maximum of 18 electrons. Now, this one comes with conditions. This one comes with conditions, but we will be able to talk about those conditions later on. So we can proceed. So when we look at the PowerPoint, basically it shows what we were doing, how to calculate the number of electrons in the first shell. The maximum is 2, the second shell the maximum is 8, and the third shell the maximum is 18. So the first shell can only hold up to the maximum of 2 electrons, the second shell 8, and the third shell 18. Then there is a condition. There is a condition here. There is a condition. Where is my? So there is a condition. So there is a condition. They're saying although the third shell can theoretically hold up to 18 electrons, it is more comfortable with a minimum of only 8 electrons. Hence, for potassium and calcium, the 19th and the 20th electron respectively are put in the fourth shell. So I'm going to demonstrate the meaning of that statement. So the third shell, they are saying for the third shell, it is comfortable with less than 8 electrons, meaning I'm going to use now I'm going to use this. So this is electron, then we have 18. So what is the meaning of this condition? What this condition basically means is that if we have electrons that are more than 8 and electrons that are less than 18, then they cannot be put in the third shell. So the third shell can only hold 8 electrons or less, or 18 electrons only. So the maximum is 18. If you have anything less than 18 and more than 8, then you cannot put in the third shell. So we're going to demonstrate this in the coming exercise. So drawing of electronic structures, we focus on the proton number. The proton number, which is also equal to the electron number, because this is an atom. So in terms of the steps that we should follow, first thing we have to do is we determine the proton number, like we were doing in the previous lesson, which was lesson 1. We use the formula 2n squared to determine the number of electrons that should be located in a particular shell, and then we write the electronic configuration, and thereafter we draw the electronic structure. But as we draw the electronic structure, the key thing is never should we leave out the nuclide notation. So the nuclide symbol or the atomic symbol should be put at the center, and then we begin to draw the structures. Let's look at the drawing of the sodium atom structure. So when we look at sodium, it's 2311. And then we have the proton number, which is 11. So what we have here is just a breakdown in terms of what we're supposed to, the steps that we're supposed to follow as we draw this, the structure of sodium atom. So using the whiteboard, I want to demonstrate how to do it, but I will start with the basic ones. Let me clear this. So I will start with the basic one, and the basic one is hydrogen. So we have hydrogen. When you check hydrogen on the periodic table is 1, 1. Therefore, your P for hydrogen, which is equal to the E, is equal to 1. So when you're drawing the structure for hydrogen, so we draw the first shell, that is the first shell, because we have 1 electron. So they are emphasizing that the first thing to do is to write the symbol at the center, so that is hydrogen. Then hydrogen only contains 1 electron, therefore you can only put 1 electron for hydrogen, so that is hydrogen. The second one is helium. So helium, when you check on the periodic table, you find that helium is H, capital H, small letter E. Then you have 4 on top, you have 2 down there, meaning your proton number, which is equal to the electron number, is equal to 2. So you have 2 electrons. Then we said the first shell holds the maximum of how many electrons? 2 electrons. So the first thing you do is, before you go any further, is to write the atomic symbol. So it's capital H at the center, small letter E. Then how many electrons? So 2 electrons. So you can put the 2 electrons like that. So that is helium. Let's advance and look at oxygen, for instance. Oxygen. Let's look at oxygen. Oxygen is O, capital O, 16 on top and 8 down there. Our interest is the proton number, which is down there. So the P is equal to the E, and the E is 8. So we have 8 electrons. How are we going to distribute the 8 electrons? So we start with the first shell. So the first shell, the first thing to do is, don't forget to put the symbol, so the oxygen symbol inside. So the first shell will get 2 electrons. The first shell will get 1, 2. So when you check your electron numbers, you have 8. From the 8, when you subtract the 2 that you have used, you subtract the 2 that you have put in that shell, your remainder will be 6. Then you go to the second shell. So that will be a second shell. Now, knowing that the maximum electrons to be put in the second shell is 8 and 6 is below 8, then it's okay, we can put the entire 6 in the second shell. So get 6 electrons, that is 1, 2, 3, 4, 5, 6. So that is for oxygen. Let's look at argon. Let's look at neon. So neon will focus on the proton number. Neon is capital N, small letter E, and you have a 10 down there, meaning your P, which is equal to the E, is equal to 10. So how do you distribute the 10? So you know that the first shell should always hold the maximum of 2 electrons. So that is our first shell. Remember to put the symbol. So capital N, small letter E. Then we put the 2 electrons. So we have 1, 2. So you have used 2 electrons, meaning you have to subtract from the remaining 10. So you subtract -2, your remainder will be 8. So if you have 8, you know that the maximum number of electrons to be put in the second shell is 8. Therefore, it's okay to draw the second shell. So in the second shell, that is where we're going to put the remaining 8. 1, 2, 3, 4, 5, 6, 7, 8. And the third shell, the second shell is full. Now imagine a situation where we are given sodium. So allow me to get rid of oxygen and hydrogen, so that we just remain with neon and helium. So imagine a situation where you are given an element or an atom such as sodium. Sodium is capital N, small letter A, and our interested number is 11, meaning the P is equal to the E, and that is giving us 11. So in the first shell, we know that we're supposed to put 2 electrons. So first shell, remember not to forget putting the symbol. So N, A. Then in the first shell, you put 2 electrons. So 1, 1, 2. Subtracting the 2 from the remaining, from the 11, subtracting the 2, we'll have a remainder of 9 electrons. Now in the second shell, we know that the second shell can hold the maximum of 8 electrons, and it's possible to get 8 from the 9. Therefore, we'll put the 8, 1, 2, 3, 4, 5, 6, 7, 8. So what happens now is you subtract the 8. You subtract the 8 and you remain with the 1. So where is this one going to go? And that is where now the third shell comes into play. So remember, we said the third shell can hold anything less than 8, but anything between 8 and 19 and 18, sorry, it cannot hold. So a 1 is less than 8. So therefore we can put the 1 in the third shell. So the third shell, remember, it can only hold anything below 8 and 18. What is between 8 and 18 you cannot put in the third shell. So the 1 goes there. That is the sodium atom electronic structure. Allow me to clear this part so that we look at another complex structure. So take for instance, we are given argon. We are given to draw the electronic structure for argon. So argon is A, capital A, small r, and we have 18 down there. So we go for the first shell. So the first shell, remember to put the atomic symbol at the center. So A, R. So the first shell will hold 2 electrons. So put 2. So what happens is your P, which was equal to the E, is 18. So when you subtract the 2 from the 18, you remain with 16. And you know that the second shell can hold the maximum of 8. So we put 8 electrons in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. So we subtract the 8 that we have used. We subtract the 8 from the 16. Our remainder will be 8. And when we come back to the rule here, we know that 8 is what we can put there. So it's okay. We can put the 8. So we draw the third structure, and we put the remaining 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that is the structure of sodium atom. So coming back to this, with that given understanding, it will be very easy for us to follow what was happening here up until we get this structure of sodium atom. Similar example is given for magnesium. We follow the same procedure. We are going to have this structure. So the most important thing is to understand the maximum number, how much electrons should be located to a certain cell, to a certain shell, and to what capacity, and so on and so forth. So from here, we can now talk about what is known as the electronic configuration. So electronic configuration is just the systematic arrangement of electrons in the shells of an atom. So when we look at sodium, it comes with a notation. So it's just a notation that we use. So when we look at sodium and we want to write its electronic configuration, so it is written like this. So in the first shell, you have 2 electrons, then you say comma. In the second shell, you have 8 electrons, comma. In the third shell, you have 1. So a 2, 8, 1 is the electronic configuration for sodium atom. Argon is going to be 2, 8, 8. So that is the electronic configuration for sodium, for argon atom. So that is the principle when it comes to the drawing of electronic structures. Just to look at the most complex on the electronic structure. Remember, we said we're going to focus on the first 20 elements. So in a situation or in a scenario where you are given potassium with a proton number of 19, therefore P and your E is equal to 19. It's equal to 19. Now we want to draw the structure. So the first shell, as usual, we'll put 2 electrons. The first shell we'll put 2 electrons. Remember not to leave out the symbol, so it's capital K. So the first shell will hold the maximum of 2 electrons. So we subtract the 2 from the 19. We subtract the 2 from the 19. We remain with 17. From the 17, it's possible to get 8. Therefore, the second shell will get 8. The second shell will get 8 electrons. So say 1, 2, 3, 4, 5, 6, 7, 8. So we subtract the 8 that we have put in the second shell, subtract 8. What will be the remainder? So the remainder will be 9. So you're in the third shell. So the third shell should always take you to this principle. Remember, you can only put less than 8 or 18. So what we have, which is remaining right there, is a 9. And a 9 is beyond 8 but less than 18. So we cannot put this. Therefore, we can only get 8 from the 9. So in the third shell, we're going to put 8. In the third shell, we're going to put 8. 1, 2, 3, 4, 5, 6, 7, 8. And we subtract the 8 that we have used. What will be the remainder? The remainder will be 1. So the 1 that remains goes in the fourth shell. Goes in the fourth shell. And therefore, the electronic configuration for potassium will be 2, 8, 8, 1. So basically that is how you come up with the electronic structure for potassium. So coming back to the PowerPoint, we have the electronic configurations for the first 20 elements. So that is the table that we have right there. So we have the electronic configuration for the first 20 from hydrogen to calcium. So once you know how to arrange, then you will be following the same format, and then you just draw the structures. So for calcium, we have 2, 8, 8, 1, meaning in the first shell you have 2, in the second shell you have 8, in the third shell you have 8, in the fourth shell you have 2. We have an exercise that we have to do just to get familiar with the concept, so we can practice the concept by answering those questions. You'll be required to draw the electronic structures and write the electronic configurations for aluminium, sulfur, calcium, and phosphorus, just to test yourself. So in a situation where I know at your level it's not possible, but in a situation where you are given, let's take this example, an atom with a proton number which is more than 20, a proton number which is more than 20. Let's say we take an element A, let's use A, with a proton number of, let's say 40. Yeah, let's say 40. How can we draw the structure? So as usual, in the first shell, we're going to put 2. So now we need to do this. So in the first shell, we're going to put 2 electrons. 2 electrons. So in the first shell, we put 2 electrons. Not forgetting to write the symbol. So this is A. We put 2 electrons. So this means that the P, which is equal to the E, in this case is 40. So subtracting the 2 that we have used, the remainder is 38. The remainder is 38. In the second shell, we know that the maximum we can put is 8. So we're going to put 8 electrons in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. Subtracting 8 from 38, so subtracting 8 from 38, we remain with 30, and we are going to the third shell. So we know that the third shell can hold the maximum of 18 electrons, and looking at what is remaining, it's very possible that we can get 18 from 30. So we're going to go ahead and put 18 electrons in the third shell now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we subtract the 18, subtract the 18 from the 30. So there we cancel, remember the 2, we put a 1 there, which is a 2 and 1. So we remain with 12. So remaining with 12, it will take us back to this. Anything between above 8 and below 18. So we are now in the fourth shell. When you calculate, the fourth shell can hold the maximum of 32 electrons. So it will still come back to this. So from the 12, we can only get 8. From the 12, we can only get 8. So we're going to put 8, and we're going to put 8. I'm going to change it a bit and extend it from this side. So we're going to put 8, 8, and then the remainder will be 4. So the remainder is what will go in the last shell. we're going to have another shell. That is where we're going to put the remainder of 4. The remainder of 4. That is 1, 2, 3, 4. Therefore, the configuration for this will be 2, 8, 18, 8, 4. So I know I cannot give you something complex beyond a calcium. So it's just the first 20 elements in our case, but going beyond just to get a wider understanding, we can go beyond 18, we can go beyond 62, and we can construct the electronic structures. So that was it for today. Until we meet next time, bye bye.